Well, hello everyone. Today I want to talk about graphing rational functions. So get some paper and pencil because we're going to be doing some thinking, and thinking means connecting things. So let's have a good record of it. All right, so my example that I have here says graph this fraction. And this fraction's different from just a reciprocal expression with the variable in the denominator. I've actually got x's both in the numerator and in the denominator. So this one's a little bit more complicated. Now, what I want to do before I begin, it really is I want to factor everything because sometimes there's some simplification that'll take place with factoring. But let me factor everything first. So let me factor the numerator. What are my factors of 6 that when I subtract them give me 1? That would be a 2 and a 3. So this is going to be an x minus 2 and an x plus 3. And then the denominator is going to be just an x plus 1. Maybe even put parentheses around that if you like. But let's see now. Let's graph this. So a couple different things. Number one, the thing that I see is I have a domain restriction. All right, so I've got a problem when the denominator, x plus 1, is equal to 0. I can't have that because you're not allowed to have a denominator equal to 0. So if I can't have x plus 1 is equal to 0, if I then solve this for x, I can't have x is equal to -1. So that will actually give me then a vertical asymptote at x is equal to -1. And I'll go ahead and graph that now in red. It's not a part of the graph of the function, but it is something that controls or has an influence on the graph of the function. So now I'm finished with that. The next thing I want to do is I want to take a look at zeros of the function. Now a fraction is only equal to 0 when the numerator and the numerator only is equal to 0. For example, if I had something like 0 over 5, well, that would be 0. If I had 0 over 0, like I don't know what that is. I can't make any decision about that yet. And we certainly can't have 5 divided by 0. That's a definite no-no. But we get the value for 0 when the numerator is 0. So now that I've factored the numerator, let me just set each one of those equal to 0. So the numerator then is going to be the x minus 2 times x plus 3. So I'm going to say x minus 2 is equal to 0. That obviously gives me x is equal to positive 2 as a 0 value for y. And then I also have this x plus 3 equal to 0. So that gives me a 0 value for y of x is equal to -3. So I've got some places now where the graph crosses the x-axis. Y is equal to 0. Remember, that's what we're doing. Y is equal to 0 when x is positive 2, which would be that point right there, and -3, which would be -1, -2, that point right there. I don't have any horizontal asymptote. So now I can just move on then to, let's say, plotting a table of values. I want to pick some values that are, man, that's a terrible vertical line. I'm embarrassed. Hang on. Let's see if I can get notability to, there we go. Nice. I like that. Okay, so let me see now if I can pick some values left and right of the vertical asymptote. So the asymptote was at x is equal to -1. So let's go to the right of -1. That would be an x value of 0, and then let's say 1, and then let's say 2, and let's say 3. And then let's go to the left of -1. Let's go to the left of that vertical asymptote. So the asymptote's at -1, so x is equal to -2, and then -3, and then -4. And believe it or not, we've already got some values in here. When x is positive 2, didn't we already say that y was 0? So I got a point right there of 0. And I'll go ahead and plot that to 0. Oh, already did. And then x is equal to -3. Well, that's 0. And then that point's, of course, already plotted. Now, to save you some time on the mathematics, you can substitute these values back in. And on your own, you'll find out that when you plug x is equal to 0 in, you get -6. And so 0, -6, that's down 1, 2, 3, 4, 5, 6. It's kind of then off the graph. It's probably like down there. When I plug x is equal to 1 in, I get -2. So let me plot that point 1, -2. That would be this location right here. And then if I do 3, I get 1.5. So about that location right there. And as I can see, this is kind of like a smooth curve, comes up from the bottom here, and then very smoothly then curves through like this. So that's what I have on the right side of the asymptote. And just to point out, right, this asymptote goes on down forever. And so my graph doesn't touch it at the ends. It skirts it, gets closer and closer and closer, but never crosses it. So let's take a look at the left side of the asymptote. When x is -2, you can do the math for that. I get 4. Well, where's that? -1, 2, 3. That's way up here. Okay, and then -3, we already got 0. And then -4, I get -2. So if I plot that point, -4 down below, I get this point right here. So it looks like it's sort of like a mirror image somehow, or somehow symmetry with respect to the right-hand side. So there's the graph. It looks something like that. Boy, that's really interesting. Yeah, maybe I would not have expected to find a graph that looked like that. That's very curious. So let me give you just a little piece of advice here. The stuff with the fractions here is complicated. It takes repeated practice to sort this stuff out. It's not going to be something that you pick up immediately, or you just look at it and go, oh, I have that now for the rest of my life. I totally understand all of that. So be patient with yourself. It's going to take some time working through these questions and bit by bit putting the pieces together and discovering properties, and then like, what was that again? And then going back and doing it a second or third time and sorting all of this out. So it's going to take some time for you to maybe wrap your head around how these things work. Don't be upset if you make some errors here or there, or don't be upset if you have to go back and look stuff up or rewatch the video even. That's perfectly okay. This is getting to be quite complicated, and so it's a skill. It's both a physical skill in terms of like, plotting the points and stuff like that, but more than that, it's a mental skill. And skills aren't something that are just memorized. Skills are something that's developed through practice. So be patient with yourself and put in the work necessary to practice it. All right, so now let's get some general principles here. A rational function would basically be a ratio of two polynomials. And so you're going to get something like f of x, the overall function, is equal to, oftentimes it's called a p of x for the top polynomial divided by a q of x for the bottom polynomial. And so sometimes you'll see it written like that. I sometimes will even write it like this. I'll actually write it like you might actually see it. It's going to be an a times x to the m plus all this other stuff, and then it's going to be divided by a b times x to the n plus the rest of it, dot, 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 dot. And we all know that we have to state that q of x, whatever the denominator is, cannot be 0. So in my example here up on top, if I take this little expression there, let's go back up and take a look at it here. Well, okay. My a right here was 1 and it's x squared, and my b on the bottom is going to be 1, and then my exponent there is 1. All I'm doing really on that one down below is I'm kind of just showing the leading term, the leading coefficient, and the variable with the highest exponent on it. And then the dot, dot, dot just means all of this, plus 1 or plus x minus 6 and so forth down below. Okay, the domain. The domain is all values except for the ones that make the denominator equal to 0. So the values that make the denominator equal to 0 are excluded. Now I want to introduce a term here that you'll come across more frequently, not formally here at this point, but I want to introduce it to you. Values that make the denominator 0 are called, it's called a discontinuity. A graph that's continuous has no stops or gaps or jumps or anything like that. Basically, you can draw it, the whole graph, without lifting your pencil up off of the paper. So like a parabola would be a completely continuous graph. But the one that we just drew wasn't. If I go back up here and look at my graph now, let me remove some of the clutter. If I look at my graph, I cannot draw the blue without lifting my pencil, or my Apple Pencil, up off of the graph, because I've got this boundary line, this red dashed asymptote here, that prevents me from drawing the whole thing all at once. So that's a discontinuity. There's more than one kind of discontinuity. An asymptote is the one that you're familiar with now at this point. But I wanted to introduce that term. So you have a discontinuity at places where the denominator is equal to 0. Now, some of those places are actually vertical asymptotes. So let's talk about now vertical asymptotes. Vertical asymptotes are what you get that, when simplified, if x equal to c makes the denominator 0, I'll abbreviate denominator there, and c is just some number. It's not a variable. If I should write if x is equal to c makes the denominator 0, then x equal to c is a vertical asymptote when simplified. So that's why I factored it originally up on top. And when I factored it, I got the denominator of x plus 1. It did not cancel out, so that fraction can't be simplified. So what I got was then x plus 1 can't be 0. So x can't equal -1. This means that I have a vertical asymptote then at x equals -1. And that's what we saw. That's that vertical line there in red. Okay, now you'll also get horizontal asymptotes. And now I need to introduce something without, normally I would like to develop it by having some practice things and then we just kind of discover the process. But in this case, it's rather technical, and let me just tell you what it is. You've got 3 different cases: number 1, number 2, and case number 3. And they go back to this way of writing the rational expression that way, like that. Okay, so remember that m is the highest exponent on x in the numerator. That's m. N is the highest exponent on x in the denominator. And then a is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. Okay, so think about those, keep those things in mind. We're going to have some relationships here now. Let me come back and center up. We've got 3 different situations. The first situation is going to be that m is less than n. In other words, the degree on top is less than the degree on the bottom. If that's true, then y is equal to 0 is a horizontal asymptote. Okay, now in the example question that we did, is the degree on top less than the degree on the bottom? Let me clean some of this up here. Is the degree on top less than the degree on the bottom? No, the degree on top is 2, the degree on the bottom is 1. So it doesn't fit that criteria. And we did not have a horizontal asymptote on that graph. Okay, second, if the degree on top is equal to the degree on the bottom, then y equals the fraction a over b. What a and b? The ones that are over here in red, the leading coefficients of the top and the bottom. Y is equal to a over b is the horizontal asymptote. So it might be something like 3/4 or 2, or something of that nature. And we didn't have that case in the top. What we had for our first example was that the degree on top was greater than the degree on the bottom. And if that's true, then there is no horizontal asymptote. And that's what we had there in our example question. Okay, so for the practice problems that you have, if you're working through a worksheet or something like that, you've got to go back and look at the degree of the top compared to the degree of the bottom, and then figure out which asymptote you've got if you have one. Okie dokie. All right, let's move on now to this one. Well, okay. Looking here, let's just put into practice what we just discussed, and that is the horizontal asymptote. Let me talk about horizontal asymptotes first. Now I need to find the degree of the top compared to the degree of the bottom. So the degree on top is 1, and the degree on the bottom is 2. So if the degree on top was less than the degree on the bottom, what's our horizontal asymptote? Do you remember? Look back up here again if you have to. It was number 1 right there. Y is equal to 0. So I have a horizontal asymptote now of y is equal to 0. Well, let me just go ahead and graph that. It's this line right here. Here, 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 here. Do a little dash line. I've got a horizontal asymptote. Okay, good. Now, done with that one. Let me go back now and let me do what I did at first, and that is factor the top and the bottom. So if I factor the top, hey, it's already factored. X minus 1, maybe put parentheses around that. Now, factor the denominator. Factors of 3 that when I subtract them give me 2. Well, it's going to be an x plus 3 and an x minus 1. Wait a second. I've seen x minus 1 somewhere before. Yeah, it's in the numerator. What do you want to do with that x minus 1? If you said cancel it out, you're correct. What does this give me? Well, kind of. It gives me 1 over x plus 3 as my simplified rational expression. Okay, didn't we have something about a simplified rational expression? Right, we had something that said we had a vertical asymptote. When simplified, the value that made the denominator 0. So x plus 3 then can't equal 0. And so then x is equal to negative 3 is a vertical asymptote. X can't equal negative 3 for a domain, but I'll do it in red here to separate it out. X equals to negative 3 is my vertical asymptote. So negative 3 now, here, back 1, 2, 3. It's this one right here. Okay, this is starting to come together a little bit. I got some boundary lines. Okay, so I got a horizontal asymptote at y is equal to 0, and I got a vertical asymptote at x is equal to negative 3. But wait a minute, I have to base my domain restriction on the original rational expression. Did I have another value that made the denominator 0? Yeah, I had the x minus 1 that was down there. So x minus 1, that one also cannot be equal to 0. So x somehow cannot be equal to positive 1, but I don't have a vertical asymptote at that place. I canceled out the x minus 1, but it's still a discontinuity. There's something going on at the graph at that location that's not continuous. It's not an asymptote either. So what is it? Well, let's play around a little bit, find out. So let's do, say, a table of values. And I might have to do a 2-column thing here because I may be out of room. So let's do x and a y. And let's just play around with values left and right of the vertical asymptote. So let's go to the right of the vertical asymptote. The vertical asymptote is x is equal to negative 3. So let's do negative 2. And then let's do negative 1. Let's do 0. And let's do 1, and let's do 2. And you can go back in and do the math yourself if you like. Here's the values that I'm getting. So if you need to, press pause in the video and run the numbers yourself, and then double check with what I give you here. So negative 2 gives me a y value of 1. 0 gives me a y value of 1/2. I'm sorry, negative 1 gives me a y value of 1/2. 0 gives me 1/3. 1, oh wait, I can't have 1. There is no value for that one, right? There's something going on there. We'll find out here in a minute. And then 2 gives me 1/5. Okay. Let's actually do this one. Let's do, no, I think that's enough. No, it's not. Let's do negative 2.5. Let's get close to that vertical asymptote at negative 3. Negative 2.5 is going to be 2. Let me plot that point first. Negative 2.5, 2. Negative 2.5, negative 1, negative 2, and then up 2. That gives me this point right here in blue. And then if I do negative 2, I get 1. And then if I do negative 1, I get 1/2, which is that point right there. And then 0 is 1/3 at that point right there. And then there's something at 1. But 2 gives me negative 1/5. It looks like that I'm getting a graph that comes around like this. And then something, 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 and then it goes on. So what happens? Can I get close to 1? Yeah. Can I get close to 1 from the other side? Yeah. Can I have 1? No. But I can get close and close and closer to it. It's just exactly positive 1 that I can't have. So if I can't have a single point, what I've got is I've got a hole. And I draw kind of a, whoops, it's not quite centered on 1. I should make it centered on 1. I draw a hole at x is equal to 1. There's a gap in the graph right there. It's like a pothole. It's a missing point. And it's only right at x is equal to 1. So this is what's called a removable discontinuity. There's a hole, there's a hole, there's a hole in your rational graph. Maybe you know that song, Hole in the Bottom of the Sea. But anyway, it's a removable discontinuity. You get a removable discontinuity when you get a factor that cancels out, like the x minus 1s did. Nice. Okay, so now if I plot some points over on the backhand side, it kind of just looks normal. What did I have? Oh, x and y, maybe negative 4. Negative 4 gives me negative 1. Negative 5. Negative 5 gives me negative 1/2. So negative 4 and negative 1 would be that point right there. Negative 5 is this point right here. And so I get this little curly thing down. Looks like that. Okay, so there we go. So now let's talk about point discontinuity. Point discontinuity says this: if I have f of x, which is the function, and it equals to p of x divided by q of x, right? Those are two individual functions, one on top and one on bottom. If x minus c is a factor of both p of x and q of x, then x minus c equal to 0, which gives us x equal to c, is a point discontinuity or a hole. You have a hole in the graph. Okay. Now, there's one other kind of discontinuity that we got to talk about, and we'll do it briefly. You'll get into it more in detail later, but it's called an oblique asymptote. An oblique asymptote really is what I would call a slant asymptote. It's not a vertical line and it's not a horizontal line. It's like a slant line. Okay, so an oblique asymptote has this quality. For f of x, and I'm going to write the rational function now differently, a times x to the m plus dot 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 dot, b over x to the n plus dot 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 dot. If that's true, if m is equal to n plus 1, if the degree of the numerator, this number right here, is one more, and only one, not two, not three, is only one more than the degree of the denominator, then there is a slant asymptote. Asymptote. You got to pronounce the p. Not really, I just do that for fun. So this one right here now has a slant asymptote. And I won't do the whole thing, but I'll set you up. The degree on the top is 2, the degree on the bottom is 1. Hey, I have a slant asymptote. I also notice that I have a vertical asymptote because it doesn't factor to cancel out the x plus 3. So x plus 3 can't be 0, so x can't be equal to -3, which means I have a vertical asymptote at the line x is equal to -3. So I got this -3 thing going on again here. This is old news now for you at this point. It's a vertical asymptote because it doesn't cancel out with the factor in the top. But I do have a slant asymptote. What's the slant asymptote? I'll tell you, and I'll tell you quickly. The slant asymptote is the equation that you get when you divide the numerator by the denominator. Say what? Yeah, you got to do polynomial long division. The numerator, x squared plus 5x plus 4, long division by x plus 3. And if we do the long division for that, we get an x plus 2 plus some remainder, blah, 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 blah. Not interested in that. I'm interested in this. And I'm going to save you the work from having to do it. This is now your slant asymptote. Y is equal to x plus 2. Well, what does that look like? It's a graph of x plus 2. So it crosses right here at 2. And then it's got a slope of positive 1, which means it would come down like this. I'm going downwards, but that's still a positive slope. There's your slant asymptote. And so the graph of the equation is going to be something to the left and the right of this, and I'll let you play with it if you like and plot some points, but that's how you would find the slant asymptote. Like I said, it's complicated. Give yourself time, be patient with yourself, do the work that builds the skill, right? So, keep pursuing the good, the true, and the beautiful. Have a good day.